this part, we'll look at how to troubleshoot a de-energized controller to determine the cause of a malfunction. We'll see how to test the controller to make sure it is de-energized, and then we'll look at how you can test the controller for grounds, opens, and shorts. Generally speaking, there are two reasons for de-energizing a controller before troubleshooting: to prevent personal injury and to prevent further damage to the equipment. For example, if there is a short in a controller, leaving the controller energized could damage the controller further. In addition, megometers and multimeters, which are the test instruments typically used to test for grounds and shorts, can be damaged or destroyed if they're used on energized equipment. After the controller has been de-energized, locked, and tagged according to your company's procedures, it should be tested to make sure that it is de-energized. You can use a voltage tester to test all three phases, phase to phase and phase to ground. After you're sure that the controller is de-energized, you can proceed with testing. We'll begin by looking at how a de-energized controller can be tested for grounds. Although one ground in a controller circuit is measurable, it has little or no effect on the normal operation of the controller. However, if two grounds occur in the same circuit, the result is a short. When a short is caused by a ground, normal controller operation is affected. So when the symptoms of a short are present, it's often necessary to test the controller for grounds. Testing a controller for grounds involves taking resistance measurements to ground for the complete controller circuits. A high or infinite resistance reading indicates that a ground does not exist in the circuit, while a low resistance measurement indicates that a ground is present. Two test instruments that can be used to test for grounds are a high-range ohm meter, called a megometer, and a multimeter that is set for resistance measurements. The one we'll look at is the megometer. There are several types of megometers. Some are powered by a hand-cranked generator, and others are line-powered. The one used in our example is cranked by hand. Before using the megometer to test for grounds, the electrician tests the instrument to make sure that it's operating properly. To do this, he clips the meter's two probes together and then operates the meter. The meter should indicate zero resistance, and it does. Next, the electrician separates the probes and operates the megometer again. This time it indicates infinite resistance, as it should. Finally, the electrician connects both probes to ground and operates the meter. This time, the meter should indicate a zero reading, and it does. Once he's sure that the megometer is operating properly, the electrician can begin testing the de-energized controller. This simplified schematic represents the control circuit of an AC motor controller with a megometer, which is represented by a circle with the letter M and the Greek letter omega for ohms inside of it. One of the megometer's test leads has already been attached to ground on the controller cabinet, as indicated by this symbol, which represents ground. The other test lead is placed on the output of the fuse labeled A. With these connections, this portion of the circuit will be tested when the megometer is operated. In this case, the megometer indicates a high reading, so there is no ground here. To check the remaining portion of the circuit for grounds, the megometer test lead that's attached to ground is left in place, and the other test lead is moved from fuse A to fuse B. Again, the megometer's reading indicates a high reading, so there is no ground in this portion of the circuit either. In this example, these two tests for grounds are enough to cover the entire control circuit because the circuit is divided into two parts by the open start button and its open maintaining contacts. Another test that is commonly made on de-energized controllers is the test for opens. One way to test for opens is to use a multimeter set for resistance. Each component under consideration is tested by placing the multimeter test leads on the component's electrical connection points. When a component is tested for opens, the component's resistance is measured. The first step in using a multimeter to test for opens is to zero the multimeter. On this multimeter, the electrician selects the appropriate resistance range, then touches the multimeter probes together to zero the meter. Before a component is tested, the electrician disconnects one of the wires leading to that component to prevent a parallel current path. We can use a simplified schematic to see what can happen if this is not done. In this example, we'll be testing the M coil. This diagram shows the control circuit of an AC motor controller and a multimeter. The multimeter is represented by a circle containing the letters MULTI. One of the multimeter's probes is placed on the electrical connection point on one side of the M coil, and the other probe is placed on the connection point on the other side of the M coil. This symbol represents an indicating light. The indicating light is in a portion of the circuit that's in parallel with the portion containing the M coil. Unless one of the wires connecting the M coil to the control circuit is disconnected, the multimeter will measure both the M coil and the indicating light, so the reading would not be an accurate measurement of the M coil's resistance. So one of the wires leading to the M coil is disconnected. If an open does not exist in the M coil, current flows from the multimeter through the M coil and back through the multimeter. If there is an open in the M coil, current cannot flow through the M coil back to the multimeter, and the meter would indicate a high or infinite resistance. So far, we've looked at how a de-energized controller can be tested for grounds and opens. The last type of test we'll look at is the test for shorts. Testing a de-energized controller for shorts is exactly the same as testing the controller for opens, except that the expected results are different. An open results in a higher than normal resistance reading, or infinity, while the reading for a short is lower than normal. To test for shorts, the electrician takes a resistance reading for each component under consideration. For example, to test the M coil, one of the wires leading to the M coil is disconnected to prevent a parallel current path, and the multimeter's test probes are placed on either side of the M coil. If a short exists in the M coil, there will be a low resistance path through the M coil. This means that current will flow from the multimeter along the low resistance path through the operating coil and back through the multimeter. In this case, the multimeter would indicate lower than normal resistance. In this part, we'll look at how you can clean an AC motor controller. Cleaning is an important part of preventive maintenance. There are several important reasons why an AC motor controller should be kept clean. For example, dust and dirt can obscure controller problems. In other words, dust and dirt covering a component can hide its condition. Dust, dirt, or other contamination inside a controller's circuitry can also cause shorts or grounds. And if dirt gets between contacts, it can prevent the contacts from closing properly, which can result in an incomplete circuit. Another reason for cleaning a controller's contacts is that contamination on contacts can cause an increase in resistance. Increased resistance, in turn, can result in the generation of excessive heat, which can damage contacts and burn insulation. Cleaning and other preventive maintenance tasks on an AC motor controller should be performed only after the controller has been de-energized and locked and tagged according to your company's procedures. Then remove the controller's cover and test the controller to make sure that it is de-energized. While you're cleaning the controller, wear safety goggles or other protective eyewear and be sure to follow all applicable company procedures. You can clean an AC motor controller by using a clean cloth, a soft brush, or a vacuum to remove dust, dirt, and other contamination. When you're cleaning a controller, work carefully and get the controller as clean as possible. In this part, we'll look at how you can inspect an AC motor controller's components to identify potential problems. Inspections are generally done after the controller has been de-energized, locked and tagged, and cleaned. This way, the controller will be safe to work on, and contamination won't hide the condition of any of the controller's parts. When you inspect the controller's magnetic contactor, be sure to check it thoroughly for loose pins and screws and for broken parts. After you complete the visual inspection, remove the armature and movable contacts. Then clean both the stationary contacts and the movable contacts with a soft brush to remove dust and dirt. Then examine each movable contact and stationary contact to see if it is pitted or badly burned. Pitted or badly burned copper contacts can be filed or sanded until they are smooth and clean, or they can be replaced. The The contact's original contour should be maintained when it is sanded or filed, or else the contact may not close properly when it is operated. When the original contour of a contact cannot be maintained, the contact should be replaced. You should also check the face of the contactor's armature and the iron core for rust and dirt. Any traces of rust or dirt should be removed with fine-grade sandpaper. Rust or dirt could prevent the armature and core from closing completely and cause the contactor to make a noise that's commonly referred to as a 60-cycle hum. In addition, if the armature cannot close completely, resistance will increase and heat will build up, possibly resulting in burned contacts. After the contacts and armature have been examined and any necessary repairs have been made, the movable contacts can be reinstalled and properly aligned. Once the contacts are in the proper position, the contactor's armature can be manipulated by hand to check for free movement and proper operation of the contacts. After you've examined the contactor and its parts, you should carefully examine all of the other controller components to make sure that they are in good operating condition. For example, check the fuse holder clips for tightness and make sure that the fuses are the proper size and in good condition. It's also important to check the insulation on the controller's wiring. Any damaged wiring should be replaced. Silver contacts should not be filed or sanded. Filing or sanding silver contacts could remove the silver plating and damage the effectiveness of the contacts. When silver contacts are pitted or badly burned, they should be replaced. When either silver contacts or copper contacts are replaced, both the movable contact and the stationary contact should be replaced to ensure proper seating in the contactor. You may notice that a black film has formed on the surfaces of the contacts. On copper contacts, this film is copper oxide, which is a poor conductor of electricity. You can remove copper oxide by filing or sanding. The black film on silver contacts is silver oxide. Unlike copper oxide, silver oxide is a good conductor of electricity, so it should not be removed from contact surfaces. Be sure to check all the connection points in the controller with a screwdriver to make sure that they are mechanically tight. If they aren't, tighten them. After you have thoroughly examined the controller and made any necessary repairs, you can energize the controller according to company procedures. Then, make a test run to make sure that the controller is operating correctly.